right, so we talked about the half-life of a reaction. We said for a first order reaction, we said that the half-life is equal to 0.693 over K. And that equation is given on the equation sheet. And you may wonder, where does this equation come from? Well, if you take a rate law and you use calculus and you do what's called some integration, and again, you don't need to understand that. If you're like, oh, I don't know calculus, that's okay. Okay, you get this equation right here. Okay, and what this equation is called, it's not, they don't identify it as this on the equation sheet, but it is there. It is for a first order reaction. It's called the integrated rate law. Okay, and the integrated rate law is just that, is it's written exactly like this. That's how it says, how it's given on the equation sheet. Okay, where you take the natural log, that's just, again, don't worry about what that means. It's just a button on your calculator, okay? The natural log of the concentration at some certain time during the experiment minus the natural log of the concentration at time 0. So this is the initial concentration. That's equal to the negative rate constant times the amount of time that has passed. Now, what you can do with this equation, usually you don't have to solve problems with it on the AP test. Usually it's more conceptual based. Notice that if I take this part right here and I add that to both sides, I can move it over here to this side. And when I do that, I end up with an equation like this. And the reason that that is important is because you'll notice that that equation is written in the y equals mx plus b format, which we know, that this part you do need to know, when something's in the y equals mx plus b format, it forms a straight line. Okay, and we know that m is the slope of that line, and that's really, really important because notice that the m represents negative k. So you can use the slope of the line, take the negative slope of the line, and that will tell you the rate constant. That's another way to find the rate constant. Now, notice again, we have, and this is one of the most important parts of this whole unit. With that y equals mx plus b format, the y is the natural log of the concentration. So notice that it, and this is the really important part right here, is if it's a first order reaction, then the y-axis will have the natural log of the concentration on the y-axis, and then time obviously will be down here. Okay, remember y equals mx, so the x is the time factor. Okay, the key is it's a straight line when the natural log produces a straight line, and the slope will also always be negative. Okay, and again, because remember m is negative k, k is always a positive value, so when you have negative k, it's always going to be a negative value. So anytime you see a graph, and they love questions like this right now, anytime you see a graph where it has a negative slope and it's a straight line and the y-axis has the natural log of the concentration on that y-axis, you know that has to be a first order reaction 100% of the time. Okay, and then you can choose two different points on that line and do y2, remember to find slope, which is m, it's y2 minus y1 over x2 minus x1. Okay, so, and then you would take the negative of that to get the rate constant k. So that's another way you can find the rate constant. Okay, with a second order reaction, and they only have two of them. There's the first integrated rate law and the second integrated rate law. When they do that, they are in order on the AP test. So there's two integrated rate laws on the AP test. The first order one comes first, and then there's the second order one, and then they have the half-life equation for first order reactions. Those are the three kinetics equations that are given on the test. It goes, this one comes first, then they have the second order one here, which again, so you don't need to memorize them. Okay, and then the third equation they have in there is this one right here. And again, that only works for first order reactions. Okay, now notice that with the second order, the second integrated rate law, it's not natural log, it's 1 over the concentrations. So when you put it in the y equals mx plus b format, notice again that the x is still time. Here's our x component. The time will always be on the x-axis, okay? What changes clearly is the y-axis. In a second order reaction where you're going to have a straight line, instead of the natural log being on the y-axis, you're going to have 1 over the concentration on the y-axis. Okay, and then notice here that k is not a negative number, so your slope will be a positive, so you'll have a positive slope, and it will be 1 over the concentration on the y-axis. Okay, and again, you can choose 2 points if you had to calculate the slope, or they asked you, how do you find the rate constant? You choose 2 points, you figure out the slope, and that is absolutely the rate constant. And then what if it's 0 order? We know the rate of a 0 order reaction does not depend on the concentration of the reactants at all, so the rate will always be the same at a given temperature. Because the rate, I mean, think of what does a rate law look like? Rate equals K times what? Times nothing. Okay, it's just rate equals K. So the graph of the change in the concentration of a reactant of a 0 order reaction will be a straight line with a slope equal to negative K. Okay, so if rate equals K, then the graph of that will be, again, the graph of the change concentration of reactant of 0 versus time will be a straight line. So it'll just have concentration on the side, and then it will have time here on the bottom. So it's not 1 over the concentration, it's not the natural log, and then you'll have just that negative slope again like that where it's straight. Okay, so that is a 0 order reaction. Okay, so here's kind of a summary of that. You can see what's given, what's not given. The half-life ones, you don't need, if they're not given, you don't need to know them, okay? This is given on the equation sheet. The second order and the 0 order, are not. Again, they're not given in the y equals mx plus b format. Notice it says here, this is how it's given on the equation sheet. But here's basically, you always take that second part that's subtracted and you just move it over to the other side by adding it. Okay, and in both cases, it's the same thing. All right, let's look at some examples of this. Example 1, data concerning the change concentration of a single reactant A and a particular chemical reaction are calculated and tabulated below. One of the things that they do here is they don't get, because remember, one of the ways you can determine that first question, what is the order with respect to A, is to go, oh, well, is the half-life constant? So I'm starting at 1, and I'm looking, how long does it take me to get to 0.5? They don't have it. Okay, and they did that on purpose. Okay, they don't want you to be able to do it that way, but that absolutely, without even looking at the graphs, that's one way you could know is if you see how, if you're seeing 1 to 0.5 and then 0.5 to 0.25, etc., then you could. But notice the numbers they purposely chose, there's really no way to determine is the half-life constant or not. But, of course, they give you data, okay? And the data shows that the concentration here, I'm looking at the y-axis here, is not a straight line, okay? But then the natural log of the concentration, we can zoom in on that a little bit. Notice that, and again, it may not be perfectly straight, but it's going to be really, really close, okay? And usually it is perfectly straight. It looks like it might be a little bit off from perfectly straight right there at the end, okay? But absolutely, what is the order with respect to A? It is certainly first order, okay? And if it is first order, how would we justify that? Because the graph of natural log of the concentration, or I guess A, not X, versus time is a straight line with a negative slope. Okay, and then write the rate law for the reaction. So rate equals K times the concentration of A. And then now they say calculate the rate constant for that reaction. So remember that the rate constant is absolutely the value, the negative slope of that line. So I'm just going to choose, usually I choose the two that are the farthest ones apart. So natural log looks like it is 0 and 2.5. So y2 minus y1. So that's going to be negative 2.5 minus 0 over, and it looks like we're at, for the x's, looks like we're at 25 and 0. So over 25 minus 0. Okay, so that equals obviously negative 2.5 over 25, which is equal to negative 0.10. And then remember that the rate constant is the negative slope. So remember, its rate is equal to the negative, or the rate constant is the negative slope. So we have to take the negative of that. So the k value is going to equal 0.10. Now, in terms of units, we've got time. We know that it's that with a zero order reaction, or excuse me, a first order reaction, we know that it's just the time to the minus 1. So our time is in minutes. So it'd just be 0.10 and then minutes to the minus 1. And now it says, what's the concentration of A after 30 minutes? Now here's where the integrated rate law is nice. Okay, so let's go back to the way that it's written up here. So we want to know, they want to know what's the concentration after 30 minutes. So what they're looking for is they're looking for that value right there. Okay, and to find that, we obviously need to know all the rest of this, and then we're going to solve for the concentration at time 30 minutes. So we need to use that equation. So we need the natural log of the initial concentration. So the initial concentration is, here's our time 0. Our initial concentration is 1. So we're going to take the natural log of A at time 30 minutes minus the natural log of, and the concentration of A initially is 1. Okay, and that's going to equal, let's make sure we have it correctly here, negative, we can see it's right here as well, negative KT. So we're going to take negative K, which again, 0.10 minutes to the minus 1, and then our time is 30 minutes, they say. Okay, and now we just need to go to our calculator. So the natural log of A at time 30 is going to equal negative, follow along with me, I'm starting right here, negative 0.10 times 30, and then I have to move this whole thing over to the other side. So that's going to be plus, and just find the natural log button on your calculator. Just says ln, the natural log of 1. Okay, and that is equal to negative 3. So to find our answer, we don't want the natural log of the concentration. We want the concentration. So here's where, again, knowing your calculator well helps. Here's where you want to do the opposite of natural log. To get rid of natural log, so you're going to take right above your natural log button, you probably have a button that has a lowercase e to the x. That's what you're going to push. And that's again, is the inverse of natural log. So I'm going to hit e to the, and then I'm just going to put that answer back in there, negative 3. Okay, the concentration of A at time 30 minutes is equal to 0.0498. Okay, and that's, now, hey, where's the units in there? Don't worry about units, but clearly it's concentration, so it's molarity. So 0.0498. Now, first of all, let's think, does that make sense? Okay, because at 25 minutes, right, we're at 0.08. So does it make sense that after 30 minutes, we're basically at 0.05? But when I get done with a math problem like that, especially one where I really don't understand the math, the natural log, and the e to the x, I just want to check and make sure, is my answer logical? Because what if I got like 8,000? Okay, that doesn't make sense. But if I'm at 0.08 at 25 minutes, I would expect it to be a little bit lower than that at 30 minutes. And it is. At 30 minutes, it's at 0.0498. And so I'm like, yeah, that's a reasonable answer. Even without doing the math, if I were to ask you even to predict, what do you think it's going to be at 30 minutes? Maybe 0.04, maybe 0.0, it didn't even go down by half here, so maybe 0.05. Yeah, okay, well, that's what we got, was right around 0.05. Okay, example 2. A compound found in food, compound X, is known to decompose over time. To study the reaction, a student monitors the molar concentration of compound X in solution at constant temperature. After collecting and analyzing the data, the following linear graph was created by plotting X versus time. The student proposes that the reaction is zero order with respect to compound X. Do you agree or disagree? Well, they've only given you one graph, and we don't see the initial number here, but we do see that this line right here is, again, I didn't draw it straight, but that is a straight line. So the concentration versus time is absolutely a straight line. Not the natural log, not 1 over the concentration. That would be second order. So the student proposes it's zero order. Do you agree or disagree? Absolutely. I'm going to agree with that. Okay? And then again, you're just going to say, because a zero order reaction makes the concentration versus time have a straight line with a negative slope. Okay? And if that's the case, then what is the rate constant? Rate equals K. Okay, and then in part C, determine the value of the rate constant for the reaction. Include units with your reaction, or with your answer. Well, the rate is equal to K, the rate constant. So we have some data here in our table here. So if we come back up here to where we talked about zero order reactions, okay, the AT versus time is that straight line. The slope is equal to negative K again. And let's look at what we underlined up here. The graph of the change in concentration of a reactant versus time will be a straight line with a slope equal to negative K. Okay, so if the rate is equal to K. So if we can get the slope, that'll be equal to negative K. And then once we know negative K, we take the negative of that to get the rate. Okay, so we're going to take the value of the rate constant. We'll figure out that, and then again, they don't ask us for it, but then we could also use that to get the rate. Okay, so we're going to choose 2 points on the line. Let's go 9. Again, just to make it easier on ourselves, because it's a straight line. I'm just trying to find whole numbers here. It looks like I may not find them. So let's say this. And again, you're estimating here, so they're going to give you a wide range of answers here. So let's use that point because that's 5 and 10. And I don't know, let's just use, no, that's 2. No, we've got 9. Okay, so y2 minus y1. So that's going to be y2 is our farther one. Again, it doesn't really matter how we do it, but we just have to be consistent with when we do the slope. So y2 minus y1. So our y2 would be about let's say 2.0. So 2.0 minus 10.0. So 2.0 minus 10.0 would be our y's, and then for x, it would just be 9 minus 5 over 9 minus 5. So 2 minus 10 is negative 8. 9 minus 5 is 4. And negative 8 over 4 is obviously negative 2. And it is a zero order reaction, okay? With a zero order reaction, again, the rate is equal to the rate constant, okay? In this case, so let's check and make sure again here. What did we see? That the slope is equal to negative K. So we just calculated the slope. The slope is negative 2. Okay, so therefore, if the slope is negative 2, that equals the slope, okay, then our rate constant is the negative of that. So K is going to equal 2. And let's think about our units here. This is concentration, and this is time in hours. So that's going to be molarity on the top and hours on the bottom. So this is 2 molarity per hour. Again, not a tough question, but a lot to do there. A lot of things that you have to remember there. That would be the value of K. And again, that's also the rate in this case. And then D, the student claims that if the experiment were conducted again at a higher temperature, the value for the rate constant K would increase. Do you agree or disagree with the student's claim? Justify your answer by comparing the slope of the original line above to the slope that would result from the higher concentration conditions. First of all, we know that yes, that is true, okay? Do you agree? So absolutely yes, I would agree. Increasing the temperature would increase the rate constant, which means that instead of 2 molar per hour, it would be higher than that. So instead of the line being like this, we would need that line to be steeper, okay? Which means that the line would be, for example, instead of -2, we'd want it to be like -3. Okay, so that would be at the higher temperature. Okay, so justify your answer by comparing the slope of the original line to the slope. So the new line would have a larger, a more negative slope, which would result in a larger rate constant. Okay, so that would have a more negative slope, or therefore basically a steeper line. Okay, so agree, K would be larger because the slope of the line from the second experiment would be steeper, or again, a more negative slope than the first experiment. Okay, last one. A student claims that a reaction is 0th order with respect to C2H6O, and that the rate constant is 1 molar per minute. Okay, so if the rate constant is that, we also know that for a 0 order reaction, rate equals K. So if it's 1 molar per minute, that's the rate constant. It's also the rate. Is the following graph consistent with the student's claim? Justify your answer in respect to the graph's axes and the numerical value of the slope of the line. So so first of all, it is just concentration and it is time. So that's fine. If it was natural log or if it was 1 over the concentration, then it would be a no. Okay, but that does represent, it's a straight line with a negative slope. It has concentration over on the y-axis. So that represents a 0 order reaction. Okay, how about the slope though? Okay, let's look at, and again, let's just choose 2 points. So we're going to go y2 minus y1. So that'd be 0.4. And I'm choosing this point right here and that point right there. Minus 1 over, and then x2 minus x1, which would be 0.6 minus 0. So that would give us negative 0.6 over 0.6. And that, remember, that equals the slope. And the slope is equal to negative k. So therefore, the slope would equal 1. Okay? And that's what they have. So, is the following graph consistent with the student's claim? Absolutely yes. And how would you justify that? Because concentration versus time produces a straight line. So concentration versus time produces a straight line. And the negative slope equals the rate constant. So both of the things that we need are there. So yes, that is the correct response.